Welcome to the deep dive. If
Yeah.
you're listening to this, you likely navigated around a coffee table, walked through a doorway, and sat down in a chair today without consciously thinking about the complex 3D geometry of those objects even once.
Right. Yeah. You intuitively knew how far away everything was. It feels completely effortless to you.
Exactly. I mean, millions of years of evolution gave humans this highly tuned, continuous 3D spatial processor right in our heads. From the moment we open our eyes, we're constantly passively mapping the depth, the dimensions, and the physical layout of our environment.
We don't have to calculate the math. We just, we feel the space.
We really do. But then we look at artificial intelligence. When we have these massive models that can write a beautiful symphony, pass a bar exam, or code an entire application in seconds. But the moment you put them in a digital simulation of a normal living room, they basically trip over the coffee table.
Yeah, they just do not understand physical space at all.
It's wild. So today's mission is to explore how that paradox is finally being solved. We are looking at the absolute bleeding edge of artificial intelligence. Specifically, we're diving into foundational state-of-the-art generative AI research.
It's a huge step forward.
It really is. And our stack of sources today is anchored by a groundbreaking new research paper titled Ouroboros-Spatial, Closing the Data Model Loop for Spatial Reasoning.
Anyone tracking where artificial intelligence is heading next really needs to pay attention to this framework. I mean, understanding 3D space is the major bottleneck right now for multimodal large language models, or MLLMs.
Right.
If we want truly autonomous driving or a robot that can navigate a messy kitchen to put dishes away, the AI has to understand 3D geometry and object sizes just as effortlessly as you or I do.
And what this paper reveals is that the way developers have been teaching AI about space is, well, it's fundamentally flawed. But even better, it shows us the fix. Researchers basically made the AI act as both the student and the teacher simultaneously. And by doing that, they took a relatively small model and made it drastically outperform trillion-parameter tech giants using just a tiny fraction of the data.
To really appreciate the elegance of their solution, we first have to understand why the old method of teaching AI was failing so badly. Currently, when developers want to teach an MLLM about spatial relationships, they rely on massive static data sets.
Like the VICA data set, right?
Exactly, yeah. Take a recent prominent one like VICA322K. It is essentially a database of over 300,000 spatial questions and answers, all generated from annotated 3D video data.
Okay, let's unpack this because static really is the operative word here. Developers take these hundreds of thousands of questions and just dump them onto the model during the training phase.
Pretty much.
It's like a teacher forcing a student to do 10,000 flashcards, where half are 1 + 1 = 2 and the other half are quantum physics. It's incredibly inefficient. The student's evolving capability just isn't respected at all.
Right. That scattershot approach is incredibly inefficient. All those training samples are treated totally uniformly by the system. The static dataset has no mechanism to care if the model has already mastered basic counting, or if a complex 3D geometry question is just entirely beyond its current capability.
The student's capacity is ignored.
Completely ignored.
Yeah.
And the source material details some, frankly, hilarious but deeply problematic failures that happen when you use these static pipelines. They essentially force the AI to learn things that are objectively false.
Yeah, the researchers dug into a standard rule-based data set and pulled up one highly revealing example of a living room that I like to call the invisible dishwasher.
Oh, the invisible dishwasher is a prime example of the hallucination problem.
Yeah.
So the researchers looked at a specific room scene from a widely used data set. I think it was ARKit scene 410-48225. That's the one. This digital scene comes with metadata like a structured spreadsheet listing everything theoretically located in that room, and the metadata explicitly notes the presence of a dishwasher. Because the static pipeline relies on this metadata, it automatically generates a training question for the AI. In centimeters, what is the longest side of the dishwasher?
And the ground truth answer, provided by the spreadsheet, is 88 centimeters. Which, sounds perfectly reasonable. We want the AI to learn how to measure objects.
It does, until you examine the visual input the AI actually receives to answer that question. The AI is trained on 32 uniformly sampled video frames of that room, but in those specific 32 frames, the camera only captures a dining area and some wooden kitchen cabinetry.
So no dishwasher.
The dishwasher is completely out of frame. It is entirely invisible to the AI.
Let me make sure I'm wrapping my head around the neural mechanics here. The AI is looking at a picture of a dining table. It is being asked how big the dishwasher is, and then the training system punishes the AI until it correctly answers 88 centimeters.
Exactly.
It's literally being trained to hallucinate an object that isn't there, just because a flawed spreadsheet said it should be.
Worse, the AI is actively updating its internal neural pathways to ignore its own digital eyes. It learns that visual evidence doesn't matter, and that guessing based on hidden contextual clues is what gets rewarded.
That is wild.
And the researchers found another glaring issue in the static data. They call it the sofa illusion. In another scene, I think scene 410-48093, the static pipeline generates a question asking, how many sofas can you find in this area? And the official answer is 3.
But when you actually look at the video frames,
You see one standard sofa and 2 smaller armchairs arranged around a fireplace. The 3D annotation from the dataset lazily grouped all upholstered seating under the single label sofas.
even though armchairs and sofas have entirely different dimensions and visual profiles, so if a human looked at it, they'd say 1 sofa.
Right.
But the AI is forced to say 3. It's not learning how to visually count or categorize objects. It's being forced to memorize arbitrary, incorrect annotation rules.
This represents the fundamental limitation of static pipelines. They decouple the question generation from the visual reality the model actually experiences.
Because static datasets are so deeply flawed and quite literally teach AI to hallucinate, the researchers realized they needed a dynamic solution. Which brings us to Ouroboros-Spatial.
Yes.
Named after the Ouroboros, the ancient symbol of the snake eating its own tail. It represents a closed, self-evolving loop.
The architecture they built mirrors that concept beautifully. Instead of a linear pipeline where a dump of data goes in and a trained model comes out, they created an iterative, self-contained loop where the model plays 2 distinct roles simultaneously.
So instead of a static textbook, the model is essentially playing a game of ping pong with itself.
That captures the dynamic perfectly. In this framework, the model splits into 2 roles, the proposer and the solver. Let's break down how the proposer, which acts as the teacher, functions. It uses those same 32 video frames and the 3D metadata.
The proposer's job isn't just to ask questions blindly, though. It generates spatial questions, but then it does something really clever to guarantee accuracy. It generates executable Python code to find the exact, mathematically correct answer from the 3D metadata.
Right. And executing deterministic Python code against the structured metadata ensures the ground truth answer is absolutely precise. The metadata acts like an architectural blueprint.
Yeah.
The Python code queries that blueprint to extract the factual mathematical distance or dimension. It's not an AI guessing the answer, it's a hard-coded program extracting an indisputable measurement.
But wait, getting the exact measurement from a blueprint doesn't solve the invisible dishwasher problem. Just because the Python code found the dishwasher in the metadata blueprint doesn't mean it's actually visible in the video frames the AI is looking at.
The proposer anticipates that exact issue, and this is where it performs its most critical function. It acts as a visual filter.
Okay, how so?
After it generates the question and runs the Python code to get the factual answer, it takes that pair and cross-references it against the actual 2D visual frames. It uses visual grounding techniques to ask itself, is this 88-centimeter object actually visible in these 32 images?
Oh, wow. So if the object is missing from the camera view, or if the question relies on some weird language shortcut instead of actual visual reasoning, the proposer catches it and throws the question out.
It completely eradicates the hallucination training. Once the proposer compiles a batch of verified, visually sound questions that can actually be answered by looking at the images, it hands them over to the solver.
The student.
Exactly. The solver then fine-tunes its spatial reasoning capabilities based solely on those high-quality, reality-checked questions.
But having perfectly accurate questions doesn't matter if they are the wrong difficulty for the student.
Yeah.
I mean, a college-level calculus question might be mathematically perfect, but giving it to a kindergartner is useless.
Right.
The system needs a way to figure out the AI's current grade level, so to speak.
And finding that correct grade level is how they solve the flashcard problem we discussed earlier. The system needs to operate in what we can call the Goldilocks zone. When the solver answers the questions, the system grades them into 3 distinct categories: easy, hard, or frontier.
Frontier being that sweet spot, right on the edge of what the AI currently understands.
Precisely. Easy means the model has already mastered that spatial concept. Hard means the question might be too noisy, ambiguous, or just completely beyond the model's current capacity to comprehend. Frontier is where the actual cognitive development happens.
Makes sense.
The solver essentially compiles this feedback, instructing the proposer to stop generating easy filler, avoid the confusing hard stuff, and focus purely on the frontier for the next round of generation.
Okay, I have to push back here. Wait, Isn't calculating the difficulty of thousands of different questions incredibly computationally expensive? If the AI has to stop, run a bunch of separate evaluation models, and deeply analyze whether a question was hard or not, how does it know the difficulty without burning through massive amounts of extra computing power?
The researchers faced that exact hurdle. What's fascinating here is the incredibly elegant zero-compute shortcut they discovered. They do not run any extra valuation tests. They leverage a metric called token-level prediction confidence.
Token-level prediction confidence. Break that down for us. What does that actually mean under the hood?
Well, when an AI generates an answer, say the number 88, it doesn't just guess a complete word blindly. It constructs the answer piece by piece, or token by token. For every single token it generates, the AI's neural network calculates a statistical probability of how confident it is that this specific token is the correct next step. It's built into the fundamental math of how these models work.
So the AI naturally scores its own confidence on a scale for every single syllable it spits out.
Yeah. The researchers simply take those existing confidence scores and calculate the geometric mean. Essentially, they multiply the probabilities of all the tokens in the answer together, which provides a clean, overall confidence grade for the entire sentence.
They're just scooping up the math the AI is already doing during its normal forward pass.
Exactly. If the geometric mean of the answer's probability is very high, like above 0.9, the system automatically tags it as easy. The model was highly confident it knew the geometry. If the probability is very low, below 0.1, it tags it as hard. The model was basically just guessing in the dark. Anything falling in between is mathematically defined as the frontier. Because they extract this data directly from the standard training pass, it requires literally zero extra computing cost to grade the difficulty.
Zero extra cost. That is the kind of engineering elegance that genuinely changes industries. The snake eats its tail perfectly.
It really does.
The proposer generates verified questions, the solver answers them, and passively tags their difficulty using its own internal math. That feedback loops back to the proposer, and the next batch of questions gets tailored to exactly what the solver needs to learn next.
It creates a truly self-evolving training distribution, but the theoretical elegance of an architecture only matters if it translates to real-world performance.
Which brings us to the actual result. The researchers applied this Ouroboros loop to two open-source models, Qwen3VL4B and Qwen3VL8B. The 4B and 8B refer to the number parameters 4 billion and 8 billion.
Right.
In the current landscape of artificial intelligence, those are practically featherweights compared to the massive proprietary models. But the data efficiency they achieved is staggering.
We are looking at a profound David versus Goliath scenario here. Consider that static data set we mentioned earlier, VICA, with its 322,000 training samples. The Ouroboros models were trained on just 25,600 samples across 4 rounds of self-evolution.
Wait, you mentioned they only used 25,600 samples for this entire loop. That is 10 to 100 times less data than recent curated data sets. That's practically a rounding error for most modern AI training runs. How is this tiny model competing with the giants using a fraction of the data?
By ensuring every single data point is verified, visible, and sitting right on the learning frontier, the results completely rewrite the leaderboard. The 8B model hit a record average score of 63.3 on the VSI bench.
And VSI bench is the rigorous standard benchmark for testing spatial reasoning.
Right. It didn't just edge out other small open-source models. It beat the massive closed-door proprietary systems. It beat Gemini 3 Pro. It beat GPT-5.
That's incredible.
An 8 billion parameter model trained on roughly 25,000 samples is outsmarting the biggest models on the planet when it comes to understanding physical space.
Here's where it gets really interesting, though.
Yeah.
How do we know it didn't just memorize the answers? Like knowing a standard desk is 1.5 meters wide. If I show you a picture of an office and ask how wide the desk is, you might just guess 1.5 meters because that's standard, not because you actually measured the pixels in the image.
Disentangling genuine spatial cognition from clever language guessing is a major challenge in AI evaluation. To prove the model wasn't just relying on language priors, the researchers ran the models through the VSI debiased benchmark.
Okay.
This specialized test intentionally strips out standard measurements and language shortcuts. The objects are unusual sizes or placed in non-standard configurations. The AI must rely purely on visual spatial reasoning to get the answer right.
So if it was cheating, its score would absolutely plummet on the debiased test. What were the results?
The models only dropped about 6 points on the debiased benchmark. They maintained a massive lead over the competition, proving definitively that the self-evolving loop taught them genuine, robust spatial cognition. They are actually calculating the geometry of the scenes based on the visual input.
That is wild. And just to put a bow on the performance aspect, it didn't sacrifice its general intelligence to get there, right? Sometimes when researchers hypertune a model to be amazing at one specific task, it essentially forgets how to do everything else.
The researchers tested for that exact degradation. They evaluated the models on general video understanding benchmarks like VideoME and multi-image reasoning tests like MV-Bench.
Yeah.
The Ouroboros models maintained, and in some categories slightly improved, their broad general reasoning skills. They didn't overfit to the spatial data, they just integrated a massive new capability into their existing toolkit.
Stepping back from the benchmarks and the raw data points, why does this leap in spatial intelligence matter for you, the listener? What happens when an AI can suddenly understand the 3D space of a room just by looking at a standard 2D video?
The immediate applications are profoundly positive. Think about the implications for assistive navigation for visually impaired users. Currently, an AI might be able to announce, "There is a chair in the room."
Right?
But with this level of hyper-efficient spatial reasoning running on a lightweight wearable device, the AI could accurately describe the exact metric geometry of an environment in real time. It could tell a user, the chair is 1.2 meters directly ahead, and the edge of the coffee table is 40 centimeters to your left.
And the implications for robotics are huge, too. A household robot wouldn't accidentally crush a delicate object or run headfirst into a wall because it finally understands metric depth and spatial relationships without needing a massive, energy-draining supercomputer strapped to its back. The data efficiency means this intelligence can run on localized hardware.
It completely democratizes embodied intelligence, but any technology capable of perfectly parsing fine-grained indoor geometry from flat video frames carries significant dual-use implications.
Meaning there's a darker side to this level of 3D understanding.
Unfortunately, yes. If a lightweight AI can instantly reason about the exact dimensions of a space from a standard video, it means any video recorded could theoretically be reverse-engineered into a highly accurate 3D map. A quick, seemingly innocent video taken on a phone inside someone's home could be utilized for the unauthorized 3D reconstruction of a highly private space or utilized for advanced surveillance mapping.
That is a deeply unsettling implication. A 10-second pan across your living room gives a system the ability to accurately measure the distance between your personal safe and the nearest window.
The researchers who developed Ouroboros-Spatial recognized this vulnerability. To mitigate the risk, they explicitly attached a responsible use license to the open-source model weights.
Okay, so there are guardrails.
Yes. This license legally prohibits the deployment of the model for surveillance applications or the unauthorized spatial mapping of private environments.
While a license might not stop a determined bad actor, it is a necessary safeguard that sets a legal and ethical boundary for the technology's use. But setting the implications aside, the technological achievement itself is a massive leap forward.
It really represents a fundamental paradigm shift in how we approach training multimodal systems. We are moving away from brute force data dumping toward intelligent self-curating systems.
Let's summarize the incredible journey we've explored today. We started by looking at a major roadblock in artificial intelligence, the inability of brilliant language models to understand physical 3D space. We saw how traditional static data sets were actually actively harming these models, teaching them to hallucinate invisible dishwashers and miscount furniture because they couldn't check their own visual reality.
Oh, right.
But by introducing the Ouroboros-Spatial loop, a system where the AI splits into a teacher generating verified questions and a student providing continuous difficulty feedback based on its own token probabilities, researchers solved the bottleneck.
They engineered a system that operates entirely in that computational Goldilocks zone, riding the learning frontier. And they achieved state-of-the-art results using a fraction of the data, outsmarting the biggest, most expensive proprietary models on the market.
It is a brilliant piece of engineering. But it leaves us with one lingering, slightly provocative thought to end on, built right out of a limitation mentioned by the researchers themselves in the paper. Right now, this Ouroboros loop relies on highly annotated, structured 3D datasets like ScanNet or ArcitScenes to act as a safe sandbox.
Yeah, the proposer needs that underlying metadata blueprint to run its Python code and mathematically verify its answers.
The loop currently requires a controlled laboratory environment to ensure its ground truth is flawless.
Exactly.
But the stated goal of the researchers is to eventually move this architecture into unannotated, in-the-wild internet videos.
Yeah.
Just raw, messy video of the real world with no metadata safety net underneath it.
Yeah.
So what happens when this self-evolving snake stops eating its own tail in a controlled lab and is unleashed to learn the spatial geometry of the entire unannotated world? When the AI is the only one checking its own math out in the wild, how will we verify what it thinks is real?
That is the frontier we are stepping onto next.
Something to mull over. Thanks for joining us on this deep dive.